Vanadium redox flow batteries, VRFBs, are an emerging battery technology well suited for large-scale, long-duration energy storage applications. They utilize vanadium electrolyte solutions to store energy in external tanks, enabling scalability and easier maintenance compared to conventional batteries. New innovations are helping drive down costs and improve performance. This report provides an overview of VRFB technology, applications, current trends, and future outlook for grid-level energy storage. Technology overview. VRFBs consist of two tanks of vanadium electrolyte separated by a membrane. Each electrolyte solution has vanadium in different oxidation states to provide the electrochemical potential. During charging and discharging cycles, the vanadium ions change oxidation states but remain in solution. This allows the system to repeatedly store very large amounts of energy. Grid storage applications. The ability to decouple power output from energy storage capacity makes VRFBs ideal for grid load shifting, peak shaving, frequency regulation, and backing up renewables. Installations ranged from kilowatt to multi-megawatt scale. Added electrolyte can expand energy capacity as needed. Lifespans exceed 20 years with nearly unlimited cycles. Discharge durations from 4–10 hours suit grid storage needs. Current trends. Many new VRFB installations have come online globally, with capacity expected to grow over 500% from 2020 to 2025. Costs have declined but remain higher than lithium-ion batteries. Key trends include larger-scale manufacturing, additives to improve performance, and hybrid designs paired with batteries or hydrogen storage. An emphasis on longer duration discharge aims at multi-hour grid applications. Technical characteristics. VRFBs operate at ambient temperatures with no fire or explosion risks, enhancing safety. Round-trip efficiencies reach 65–85%. Degradation rates are just 0.12% per year. Rapid response times under 30 milliseconds suit grid stability needs. Limitations include relatively low energy density and high initial capital costs. Ongoing improvements target cost, efficiency, and performance. Economic analysis. Current VRFB costs are around $300–$600 per kilowatt-hour, with levelized costs of $0.12–0.17 per kilowatt-hour for lifetime operation. Cost reductions via economies of scale could reach $180 per kilowatt-hour by 2030. Costs are higher than lithium-ion but offset by longer asset life, lower degradation, and no replacement required. VRFBs are cost competitive for 4+hour utility-scale applications. Future outlook. VRFBs are expected to grow significantly in grid and renewable energy storage markets where long discharge times and low maintenance are key advantages versus alternatives. Cost declines, technology improvements, and manufacturing scale-up are critical for broader viability. Strong growth is projected in regions like China, Asia, Europe, and the US as storage needs increase. In summary, VRFBs are an emerging versatile technology able to provide safe, sustainable, large-scale energy storage for electricity grids. While costs remain high, ongoing improvements are enhancing the value proposition. With proper support and development, VRFBs have the potential to be a key grid storage asset and enable greater renewable energy penetration.